Let's start Chapter 5, Exploring Assumptions. In this chapter, we will look at the assumptions behind parametric tests, especially those based on the normal distribution. These assumptions are very important before we run tests like the t-test or regression. If the assumptions are violated, the result might be unreliable. So our goal today is to understand why these assumptions matter and how to check them properly. This slide lists what we will cover in this chapter. We will first discuss the assumption of parametric tests, mainly the normality and homogeneity of variance. This and this. We will learn how to check whether data are approximately normal using graphs, skewness, kurtosis, normality, normal test. The normality tests include the Shapiro-Wilk test. Then we will move on the Levene's test for checking if group variance are equal or not. Finally, if we find the problems, we will see how to fix them using transformations such as log, square root, and so on. Okay, next, I would like to add a supplemental explanation for the word parametric. A parametric method is one that assumes a specific probability model for the data and has a set of parameters, like the mean and variance. Example is here, the linear regression with normal errors, logistic regression with Bernoulli errors. Even when the population itself isn't exactly normal, but the central limit theorem tells us that if the sample is enough large and random sampling, then the mean will be approximately normal distribution. So we can use parametric method. Parametric method often works fine with large sample size. But if the sample size is small or skewed or heavy outlier dataset, we may need to apply non-parametric method instead. So when can we safely use parametric test? If the normality test doesn't reject normality, or if we have a large sample size, the rule of thumb is 60 over 60, parametric tests would be acceptable, usually acceptable. But when the sample size is too small or normality is clearly violated, then we should consider non-parametric method or robust method. And I would like to add one more point. Even if the normality assumptions is satisfied, the issues such as endogeneity problems, including reverse causality, remains. So reviewers may still question causal claims. So please remember that correlation is not causality. Now let's connect these to two key theorems, the central limit theorem and law of large numbers. The CLT says that no matter what the population looks like, the sampling distribution of the sample mean becomes approximately normal as the sample size increases. And LLN says that as n grows, the sample mean converges to the population mean. In other words, with more dataset and randomly drawn, then the sample average gets closer to the true average. True average means population average. And the sample distribution becomes smoother and bell-shaped. It is the normal distribution. These two theorems, these ideas, are the foundation for using the normal distribution in hypothesis testing and confidence intervals. So these two theorems is very, very important. And this figure is a standard normal distribution, the famous bell-shaped curve. The formula on the right defines the probability density function. We need to just reminder that it describes how data are distributed around the mean. And in this figure, we can see that about 68% of the data fall within one standard deviation, minus sigma to plus sigma. And 95 dataset, 95% data within 2 standard deviation, minus 2 sigma to plus 2 sigma. And 99.7% within 3 standard deviations. The key idea is that by mapping our statistics, like the sample mean, onto this known curve, and if the dataset is within here, that is within 68%, then we can check the hypothesis. We can use the normal table to calculate p-values and confidence intervals. If our dataset is here, the yellow is very difficult. Our dataset sample is here. Then this is not within the Q99%. Then we can test the hypothesis. So that is why the normal distribution is so central to the hypothesis testing. If the dataset is random and enough sufficiently large, then we rely on the two theorem. And we can test the hypothesis using this distribution. Okay, next we can check the animations. We can check what the TLT works by using the animations. To make the central limit theorem easier to grasp, imagine the rolling bias die that land on 1 and 6. The probability of 1 and probability 6 is very high. So the population distribution is not normal distribution. This is far from the even. It's clearly uneven. But if we roll the die many times and take the average each time, then something interesting can happen. So let's look at this animation. Like this. This simulation shows that even if the underlying data are not normal, the means of many samples follow a normal pattern, as long as the sample size is large enough. Like this. This is the normal distribution, very similar to the normal distribution. Even the population distribution is not normal, but we get the data randomly and the sample size is enough, then the mean is converges to the mean distribution is like this. Okay, next let's unpack the normal distribution formula just a bit. It's based on the exponential function here, noted as x parentheses, which naturally produce smooth curves that decrease gradually. The curve is symmetric. Also, the curve is symmetric around 0. And the shape is controlled by two constraints, the mean and standard deviation. Next slide is I added some explanation. for each values. And this is intuitive interpretations. This is the exponential curve, and x squared its symmetry makes monotonic decrease. And this is a constant multiplier. And this is a multiplied to 1. I mean, we multiply by 1 divided by root 2 pi, so that the area under the curve equals 1. Area under the curve equals 1, then it represents a proper probability distribution. And exponential here, exponential minus x squared divided by 2 part create a smooth bell-shaped curve that gets smaller as x moves away from 0. That's what makes the normal distribution symmetric. Why we need to multiply by 1 divided by root 2 pi is here. This part, Gaussian integral part, is the result is root 2 pi. So we need to standardize. And why pi has emerged in the when we solving Gaussian integral, brief explanation is here. The key point is transform to polar coordinate. In polar coordinates, the angular integral contributes are a factor of 2 pi. We use polar coordinate to solve this integral. Then we can solve and the result is root pi. This is the characteristic of the Gaussian integral. And we need to standard divided by 2 pi, root 2 pi. Okay, next is we add the sigma and mu. It is a general form of the normal distribution. So far, we have seen the standard normal, which has a mean of 0 and standard deviation of 1. Mu is 0 and sigma is 1 case. We have seen, but this is more general case. In real dataset, we often have any mean and any standard deviation. The formula is here. Mu is the center, the average of your dataset, and sigma controls how spread out the dataset are. If the sigma is small, the narrower and taller, and if the sigma is large, the curve is wider and flatter. This is the explanations. Firstly, think the mu again. Mu as shifting the curve left or right. It's just moving the center. We need to fix the mean at 0 and standard deviation to 1. Like sliding the entire bell curve along the x-axis. Also, a big sigma means the data are more spreading out. Sigma is the stretching or squeezing the bell-shaped curve. If sigma is small, then most people are close to the average. That is the meaning of sigma and mu. So mu tells us where the center is, and sigma tells us how wide the spread is. Okay, next, slide is the we next as the mean of population. Sorry, the sample size. Sample size. We as the sample size. Then we can write formula like this. This is the sample size. This formula means that if n is large, then the sigma, the shape of the distribution will be narrowed. So we can estimate more precisely. The standard deviation of sample mean is sigma divided by root n. So larger n means smaller variation. Larger n means smaller variations. The speed of the narrowing is the small reducing variation is the root n. So we need to gather a lot of sample. If the sample size is very large, then this part is very small. Then the data is more sharp, and our estimation would be more precise. But if the sigma is large, then the distribution shape would be wider, so our estimation would be not efficient. That is the intuitive understanding. This slide expresses the CLT in probability terms. It states that as n becomes large, the standard sample means follow the standard normal distributions. That means if we take the sample mean, subtract the population mean, and divide it by the standard error, the result behaves like a z-score. So we can use a normal table to find probabilities. For example, the chance that the sample mean lies between two values, A and B. The shaded area under the bell curve shows that probability. This is a mathematical reason why we can use z-scores, confidence intervals, and p-values in real research. The probability is here between value A and value B. The probability is here. We can assess based on this distribution. So the integral is very important. This formula is key to assess the hypothetical test. Okay, next, here is an important caution. The CLT works eventually, but if the original dataset are very strange, like this, the strongly skewed or two peaks with two peaks, then we need much larger sample size for the average to look normal. When the dataset are heavily skewed or have outliers, using a t-test with fewer than, for example, 30 observations would be risky, very risky. So we might get the wrong p-value. Maybe rejecting or not rejecting by mistake. So if data are non-normal or small sample size case, for example, the less than 30 or data looks like here, then we need to apply the non-parametric method like the Wilcoxon and Mann-Whitney test or permutation test, robust standard errors, or transform the dataset like that. Key point is that please don't both parametric tests if the data is clearly break their assumptions. If the data is not normal or sample size is small, then please don't use the parametric test. Parametric test is very simple and powerful, but they require some assumptions. Okay, example of the parametric test is here. First is t-test. Use it when you compare means and the population standard deviation is unknown case. Then we apply t-test, and the t-test assumes that student t-distribution assumes roughly IID observations, random observations, and IID observations with small samples. We rely on the t-distribution. For two groups with possibly unequal variance, prefer the Welch two-sample t-test, the modified version. It adjusts the degree of freedom. Basically, the two groups in real world, the two groups with is possibly unequal variance. So the basically Welch two-sample t-test is recommended. That is my idea. And if n increases, the t-distribution approaches to normal distribution. Next is t-test. T-test is very similar, but it assumes the population standard deviation is known. That is rare for means in applied work, so we seldom use the z-test there. So t-test is more major test because this test can be used even if the standard deviation is unknown. Sigma is unknown, typical case. But sigma is known, then for the large sample size proportion test, we can do the z-test. Rule of thumb: if n is larger than 60 or n is larger than 120, we can do the z-test. But the normality is required, so please check the skewness and outliers and consider also we need to consider non-parametric options. Okay, next slide shows a brief explanation for non-parametric. Non-parametric do not assume a fully specified distribution family, like normal distribution as Poisson distributions. Not fully specified parametric family. They often work with ranks, signs, and the empirical distribution and make weaker assumptions. But there is a caveats or cautions. The non-parametric does not mean no assumptions. Does not mean assumption free. For example, they can be less powerful than for example, they require continuity or symmetry for specific interpretations. For example, Wilcoxon test target median differences under symmetry. So all of non-parametric do not require does not mean the assumption free. So please check that. Most non-parametric method also require some assumptions like symmetry dataset or continuous dataset. So please check such. For example, you want to do the hypothetical test, the method is good or not. Please check one by one. It is not correct that non-parametric methods do not use means or variance. When to prefer them is here. A small sample case or heavy skews outliers or model misspecification is a concern case. Then non-parametric analysis would be generally better than the parametric analysis. Next slide is the examples of the non-parametric test. The chi-square test was a categorical dataset. Chi-square test is one of the most famous non-parametric tests. Two main uses is here. Goodness of fit for one variable. Does the observation distribution match the hypothesized one? This is the first one. And second one is independence. Independence between two categorical variables in contingency table. Assumptions, independent observations. Expected cell count should not be too small. Rule of thumb is over 5 for most cells. And report the chi-square statistics and degree of freedom and p-value. That is a chi-square test. Brief explanation for chi-square test. This is one representative method of non-parametric test. Another test is the Mann-Whitney test. This test is also very famous, I think. The Mann-Whitney test compares two independent samples when the outcome is ordinal or continuous and may be non-normal or outlier prone. It tests whether the two samples come from the same distribution. Strength is works well with small n and robust to outliers. Limitation is not for purely nominal outcomes. Interpretation is about ranks or medians, not mean differences. That is an important point. Some of non-parametric tests show the ranks and medians, not the mean differences. The result do not mentions about mean differences. So you need to check the interpretations. Also, that is very important point. If the sample size is enough large and it looks normal, then we can compare the mean differences. But if you apply the non-parametric test, some of non-parametric tests do not show the mean differences. Okay, before we use parametric tests, let's check the basics of the parametric test. First is the normality. The data should be roughly normal. With large samples, the sampling distribution of the mean is close to normal by the CLT. And equal variance. Equal variance is the homoscedasticity. Group variance should be similar. If not, we need to use a Welch's T or robust standard errors. And independence. Observations are independent. If we have clusters or time series, we need to adjust the model. And scale outcome should be interval or ratio. And for OLS, there is the OLS specific. Then there is another required. For example, the no perfect collinearity, exogeneity, and so on. Normal errors. Exogeneity, linearity, no perfect multicollinearity if we want to apply OLS specifics. there is some assumptions. Okay, next is how to assess the normality. For practical tools, sample size, graph, numbers, and sample size, graphs, values of skewness and kurtosis, and z-scores, standardization. Sample size is with large sample size, with large n, then the sample distribution of the mean is approximately normal by the central limit theorem. And we can check graph, QQ plot or histogram. We can use histogram or QQ plot to check the distribution is normal or not. And value of skews and kurtosis can be also checked. Skewness should be 0 and kurtosis should be 3 in the normal distribution. Okay, next. Okay, next is the applying the sample dataset, the R session. Here is as our running examples. Our biologist measures hygiene at the download music festival. The participant is 810 concert participant and over 3 days. The measure is a standardized hygiene score from 0 to 4, where 0 is very bad and 4 is very good. And we will use this dataset to practice histograms, QQ plot, and normality checks. This is the data. Okay, we can see like this. Can I check the this is our we set the working directory and install packages if you haven't. And library packages. Then we can use these graphic packages and statistical analysis packages. And firstly, we need to read the dataset like this. ELF. But as you know, there is the remove. We need to remove outlier. The dataset. This. And we can draw the histogram. Like this is the histogram, day 1. And this is the explanation of the exclude the NA dataset. Exclude. If a value is greater than 20, turn it in NA. Exclude the outlier command is here. If the data is over 20, then the data is replaced to NA. So this single line flags the outliers as missing, and we can proceed with clean plot and test. The next is here. This is a histogram. Geom histogram, and AES is here. y equals after stat density. Color is black, fill is white, and x-axis name is and y-axis name is here. Okay, this is the amount run and histogram is histogram, and y is density, x is the hygiene score, and color is black and filled by white. And the title, x title is hygiene and y title is density. This is the meaning of this command. Okay, next slide. This is the explanation. AES histogram to plot the density scaled histogram. X-axis is density. Almost the same command can be done in histogram day 2 and histogram day 3. Okay, let me check the histogram day 3. Day 2 is here. Day 2 is like this. Day 3 is here. Day 3 is like this. So it looks not normal distribution. And next slide, add kernel density curve too. Nice diagram. We can add the kernel density curve like this. This is the explanation part. Function is the norm. Norm means normal distribution. Normal distribution probability density function we add. Then 1 equals the norm. And args equals this blah blah blah. That's the mean and standard deviation. In this case, the mean is mean of the dataset and standard deviation is the standard deviation of this dataset. Then we can draw the normal distribution that adjusted to this dataset. And I think we can overlap the curve, bell-shaped curve. NARM equals 2 means the calculation is performed ignoring missing values. I wanted to ignore the portions like this, then I added this part. Okay, this is a slide, but also we can check by using part and R, then we can get here. This curve is based on the mean is this day 1 data's mean and standard deviation is day 1 data's standard deviation, because we set like this. It is same as a different day. Row 44 we run, then we get like this. Mean is here. This mean is here. And this is the sum of the result. This is the standard normal distribution, the blue line. But this is the density curve. Day 1 looks like good. Day 2, day 3, not satisfy the conditions. If one of them is clearly skewed or has heavy tails, we might need a data transformation or use a non-parametric test instead. So this visual check is our first step before running formal normality test. Day 2 and day 3 is doubtful. In my case, I would not apply the parametric test in this case. Next is QQ plot, and firstly remove the missing values and non-finite values to prevent the warnings. We always be faced with the warnings from the R software. R is very kind, so shows a lot of warnings, but sometimes we need to ignore that. The textbook do not cover this, but I recommend to clean the dataset. I tried, but the textbook does not work in that case. So the infinite, I deleted, removed infinite number value. Command meaning is here, conditional on the value of not being NA. Exclude NA in DLF Taras Day1. I explained Taras means Taras is the data set and data and the variables. We specify some variables in a data set, then variable name Taras dataset name, then we specify some variable in some data. We can specify the data. We can specify the variable in the data set. This is not finite, conditional on the value of not being infinity or minus infinity. Exclude infinity value in Day1 DLF. This is the meaning. Also, this slide shows the QQ plot. Before the QQ plot command, we can set image directory. If we add the image data folder, then we can save the image dataset in that folder, like this. And finally, QQ plot command is here. QQ plot Day1 allows qplot. We use qplot command. Sample equals Day1's DLF2 and geom equals QQ. And ggsave. Ggsave is saving the image, saving a graph created with ggplot2 as an image file. Image directory is the directory where image files are stored. And this is the file name. You do not always save the image graphs, but it is very useful, I think. The other things are okay. I think it's okay. So let's move on to the running command. QQ plot for Day1. this is the data cleaning part. Exclude the infinite number and XNA. And this is the QQ plot. Some warning message is here, but I can't. Yeah, this is a QQ plot. QQ plot for day 1. And also only change dataset name. We can see QQ plot day 2 and day 3. Day 2 and this is the day 3. Day 3 is here. I want to show the QQ plot day 1 again. That is here. This is the relatively smooth linear line, but the QQ plot day 3 case. This is not linear. Like this. Day 1, day 2, day 3. And this is the interpretation. This slide shows a typical QQ plot pattern. If both tails bend below the diagonal, the distribution is flat to right-tailed. If both tails bend above the lines, it's peaked and too heavy-tailed. If the line is S-shaped, the data are skewed. Left tail below and right tail above, then right skewed. Left tail above and right tail below, then left skewed. Recognizing these shapes help you quickly diagnose the type of non-normality. In this case, I think this holds normality, but day 2 and day 3, the shape is far from the diagonal line, and this is skewed, or there is a skewness or kytosis. We can use describe function in the PyCharm package. I'm not sure the pronunciation, I'm sorry. The quantifying normality with numbers. I mean the test. We can test the normality using the describe function. These packages. Describe, compute or display descriptive statistics for 3 variables, day 1, day 2, and day 3. Bind extracts the joins columns to create a new data frame. Describe here. ELF, extracting elements of the data frame. X, Y, extract row X and extract column Y. And here, C means extract all rows, extract columns, C, data 1, day 1, day 2, day 3. We can check the result. By using R, we can understand what we are doing intuitively. Library, site, describe result here. One row. Okay. We can check the skewness and kurtosis, standard errors, range, max, min. Describe is very useful command. We can check a lot of statistics at the same time. Then we describe day 1, day 2, day 3 at the same time like this. The result is here. Skewness is 0 in day 1. Skewness should be 0, so the skewness of day 1 is good. But the day 2 and day 3 skewness is 1.08 or 1.01. So skewness is not approximately normal. Looks like not normal. So we need to consider another method. We need to do not apply the parameter. Also another way is here. Okay, I think the next slide we explain the another way. Okay, sorry. I go back to this slide. Okay. Describe day 1, day 2, day 3. Then we get many statistics about day 1, day 2, day 3. Skewness, kurtosis, kurtosis. Kurtosis is a bit not good for day 1, but the skewness and kurtosis, both skewness and kurtosis is problematic in day 2 and day 3. We can also use the start desk function of the fasttext package. There are a lot of very good packages to show the statistical result. So you can use your preferred one. I showed the two typical case, fasttext and describe. That desk is here. You can write this. This command is very similar as before. This is the explanation. Bind ELF day 1, day 2, day 3. Extract the day 1, day 2, day 3. Statistics such as skewness and kurtosis are also calculated. If basic is true, then the only basic statistics is shown. But basic is false, then we can check the skewness and kurtosis and so on. Norm equal truth calculate a statistics to assess whether the data follow the normal distribution. So in this package, we also test the normality. This is very useful. Rounds all numerical value to 3 decimal places. That is the meaning of round command. And the next slide is start. Like this start. Fasttext and start desk. And we get here. We can see the kurtosis, skewness, and normal test here. So unfortunately, the normal test p-value is 0.03, 0.00, 0.00. So all of the day 1, day 2, day 3 is not normal. That is the result. But it is difficult point. The day 1 nearly normal asymmetric and light tailed, and day 2 and day 3 non-normal and light skewed distributions with moderate peaks. This table summarizes the central tendency, variability, and the distribution shape. The statistics of Shapiro-Wilk test of normality. Sorry, I did not explain, but this normality test is Shapiro-Wilk test here, and Shapiro-Wilk test no probability value. So in that test, this is not normal. But if we have the large sample size, then the Shapiro-Wilk test is very efficient. we easily get the non-normal result. The p-value is very small, very small. But also in large sample size, the data should be normal distribution by the central limit theorem. So in large sample size case, it would be accepted. The parametric test or normal distribution assumption would be acceptable in many cases. Also, I asked ChatGPT and ChatGPT answers nearly normal and symmetry, and day 1 would be acceptable, but day 2 and day 3 is not acceptable. Norm test P represents the p-value from the Shapiro-Wilk test, which examines whether the data follow a normal distribution. If Q2 standard errors bigger than 1, the skewness is significantly different from 0. Kurtosis is also same. The skewness is in kurtosis context. Day 1 is also problematic, but the skewness context, day 2 and day 3 is larger problems. Based on these results, the normality of day 1, day 2, day 3 was rejected. But I would like to mention that again, the larger sample size, Shapiro-Wilk test always reject the normality. But in the central limit theorem, the distribution would be asymptotically normal, larger sample size. So, in many cases, the parametric test would be acceptable. Okay, next is another example. R exam dataset. It contains the exam performance data for 100 students. The variable include exam score in percentage and computer literacy and lecture attendance rate and numeracy ability in math out of 15 and the university name. Either Dunstown or Sussex. We will use this dataset to test normality again and practice use the Shapiro-Wilk test on multiple variables. This is the install packages phase. I think we already installed these packages. For example, stats and pass text and tidyverse. If you already loaded the packages, you do not need to run here. Here we read the R exam dataset and prepare it for testing. First, we load the data with read the limit, and then we convert the variable uni into a factor because it represents categories, not numbers. Here, we specify that level 0 means Dunstown University and level 1 means the Sussex University. Finally, we run the stat-desc command from the parseText packages to get the descriptive statistics and Shapiro-Wilk test result for all 4 variables: exam, computer, lectures, and numeracy. This gives us both a central tendency and p-values for normality. Next slide is detailed explanation. Factor. Function to convert numerical data to factor type. And this is a level. Specify the level of the factor. And labels is here. Dunstan University and Sussex University. Level 0 is labeled Dunstan University. Level 1 is labeled Sussex University. Okay, we can check the R command. Import the dataset and check the stat like this. We use stat desk and round this PowerPoint, and the variable is exam, computer, lecture, numeracy. Run. Then we get the result like this. Result is here. Among the 4 variables, exam, numeracy significantly deviate. Exam and numeracy significantly deviate from normality, while computer and lectures are approximately normal. Then we can confidently say that we can apply the parametric test for computer and lectures. That is the result. Next is draw figure. We can visualize the data to confirm what the test result suggested. Here the R code for plotting the histogram and the ggplot for the exam example. We then add the histogram with geom histogram and overlay a red line representing the normal distribution curve. Next slide shows the detailed explanation like this. This part by density. This is the overlap, the density curve. Overlay the density curve. Function is normal distribution curve. And arc equal list mean equal mean blah 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 designates the parameters of the normal distribution. Mean equals mean of this dataset. Mean of exam dataset. SD standard deviation is standard deviation of exam dataset. Exclude NA. NA.rm equal true, then exclude NA. Then we get, I think, the histogram and the density function. Okay. I would like to check by R H exam ggplot2. This is the command and we can get result like this. And color is histogram color is black, and stat function is d norm. Argument is mean d exam, and the NA equal standard error is standard error, re-exam, and color is red. Then red line is drawn. This is the result. The code overlays a normal distribution curve on the histogram. Result is a bit difficult to read, but this is the first year. This may not the normal distribution because the 2 by modal. Okay. Okay, or we can also check the Shapiro-Wilk test by Shapiro-Wilk test. By parenthesis means a group data and applies a function to each group. This function split the dataset into two groups based on the factor. Here, the dataset is re-exam university, and then apply a function to each subset. In this case, Shapiro case, the command by rexam $exam rexam $uni Shapiro test run a separate normality test for each university. This is useful when we want to know if the data from each group meets the normality assumptions independently. But note that by parenthesis only works for comparing two groups at a time. For more complex designs, you will need another method like dplyr or group underbar by. This can be used only for the two group case. Okay. Shapiro-Wilk get the result like this. This is the Shapiro-Wilk test by university. This is a slide. Shapiro-Wilk normality test like this. But the Shapiro-Wilk test can easily conducted by this one, by using this one. Forgot the stat description. We can easily get the normality test result here. So we do not need to use Shapiro test command directly, but we can get the data also from this command. Normality test result is here. So we can say this normality is not violated. We cannot deny this is not there. We cannot deny the possibility of normality. In large samples, the Shapiro-Wilk test can become significant even when the data only slightly deviate from normality. Therefore, the test results should always be interpreted together with histogram and QQ-plot, and the values of skewness and kurtosis. For example, even if the test says not normal, the data may still look symmetric and smooth enough for parametric analysis. In research practice, the graphical judgment is often used and often very important as formal testing. Next is assessing the homogeneity of variance. That is the Levene's test. The assumption is crucial for the t-test and ANOVA. There are several ways to check it. The graphical first is graphical inspection. The second is Levene's test. And third is the variance ratio. Levene's test is the most common formal method. If Levene's test gives significant result, then it means that the variance are not equal, so the assumption is violated. If the result is non-significant, then the variance are approximately equal. Another simple rule of thumb is to take the ratio of the largest variance to the smallest one. If that ratio is less than 2, then we usually assume homogeneity holds. That is a homogeneity test. This is the detailed explanation for the Levene's test. The test compares the variance of two or more groups. The hypothesis of the hypothesis 0 is the group of group variance are equals. And H1 is at least one group has a different variance. That is a Levene's test meaning. Here is how it's calculated. Compute the residual from each group's mean and take the absolute values of those residuals and then run an ANOVA on these absolute values. If the resulting F test is significant, we conclude that the group variance are different. The method was proposed by Howard Levene and is widely used because it is robust to non-normal dataset. Okay. Here is how we interpret Levene's test results. Suppose the test gives a p-value of 0.2. That means there is a 20% possibility of observing this difference in variance just by chance. If the true variance are equals, so we cannot reject the null hypothesis. The variance can be considered equals. However, this doesn't mean there is an 80% chance they are unequal. It simply means that data do not provide enough evidence to claim a difference. So please remember about this. In short, the p-value is over than 0.05, equal variance assumed OK. OK for t-test. If p-value is lower than 0.05, unequal variance, use Welch's t-test or robust alternative instead. Okay, now test the equal variance using the Levene's test. In R, the core call is the Levene's test command. For our example, we run it on exam and numeracy by unit like this. If you cannot install car package, sometimes the tidyverse car package will not install or conflict with other package tidyverse. The install packages start, library start. Okay, this is the output of Levene's test. We can check this by the R Levene's test for comparison for variance. Levene's test. We can get the Levene's result like this. This is the Levene's test result, homogeneity variance test, and in this case, numeracy unit. Then this is there is a significant difference, so it's not equal variance. This result means not equal variance. For numeracy, the test is significant. Numeracy, the test is significant, so variance differ. So please use Welch's t-test. In uni, the p-value is larger than 0.05, so you can use you may be able to use we can assume equal variances. Okay, next is the collecting the dataset. When normality is poor, we can transformation the dataset. If normality or equal variance is poor, if the normality test, Shapiro-Wilk test is significant, or Levene's test is significant, then normality or equal variance is violated. Then we can try the transformation of the dataset. Firstly, we take log or take square root or reciprocal transformation. Log test reduce the positive skew and square root also reduce the skew and can stabilize the variance. And reciprocal transformation can downweight large values. We need to emphasize that the transformation changes the scale and interpretation. So when we use them, please check what the value changes, how the value changes. Be careful with log transformation in regression. The meaning of coefficient changes. For example, the income equals beta education plus blah 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 interprets beta as a level change per year of education, but log income equals beta log education case. Interpret of beta is percentage change. Interpret beta as an elasticity. A 1% increase in education is associated with a beta percent increase in income. Similarly, logging only y or only x changes interpretations. For example, percentage per unit or unit per percentage. Ensure the functional form matches domain knowledge before logging. Transformation for log is very useful, but please be careful about such kind of issues. Okay, when we use a log transformation, the interpretation changes. If we use both logs, that is the elasticity. And for example, in our domain means that I'm in the agricultural department. So for example, we use the dataset of yield and fertilizer case, log yield and normal fertilizer as it is. Beta shows what percentage does the yield increase when the amount of fertilizer increases 1 kilogram. If normality holds statistically fine, however, this is a bit strange in agronomy. The reason is this. Here is a reality check from the agronomy. An exponential response of yield to fertilizer is unusually unrealistic. Yield to fertilizer is usually unrealistic. Most input shows diminishing returns, but we take log only for yield means like this. This is unrealistic. So before transforming, what functional shape is biologically plausible is very important in my understanding. Sometimes a log or a square root on the input approximate diminishing returns. Sometimes a quadratic or quadratic style curve is better. Model truth, please check how to say that? Please check the basics of your research domain. The normality is also important, but the more important, the basics is the relationship between the, for example, in the agronomy case, yield and fertilizer basic relationships is more important, I think. Okay, so the next step, we will go to the log transform. I would like to show the R exercise, log square root and reciprocal transformation. Log +1 is necessary. +1 is important because the mathematical reason. We can transform log type like this. And we can draw log histogram like this. This is a day2 dataset. Day2 dataset. And the log shape is much better. Square root case is here. Square root case is like this. This is much better than before. Reciprocal case is here. Reciprocal case is here. It is also better. It looks better. And we can get the statistical test result for log case, square root case, reciprocal case. We check result, and result is here. I would like to check the result. Right, like this. This is the original dataset, and this is taken square root. Then it is much better for the normality aspect. Log transformation or the square root transformation, reciprocal transformation, the technique that can improve the validity and reliability of statistical analysis. But I again mentioned it should not be overused or applied blindly. This is a powerful way, but please check that it is good for the original data set or not. Then we can check. Then this transformation helps you. That is the content of the chapter 5. Thank you very much for listening. Next is chapter 6.